So the first example of conservation of momentum that we're going to look at is when two objects collide and stick together. So here you have two balls. Ball 1 is moving with the velocity of 1 meter per second before the collision, and ball 2 is stationary. And let's see what happens to their velocity after they collide and they stick together. So notice that after they collide, they both move with a final velocity of 0.64 meter per second. So this is called a completely inelastic collision, where the collision, they don't behave like a rubber ball. They stick together like putty, and they move together with the same final velocity. So this is called a completely inelastic collision. So now we're going to look at the equation that applies to inelastic collisions. So what you have is before the collision, and you have after the collision. So before the collision, let's say that you have two objects, so mass 1 and mass 2. And let's say that mass 1 is moving with the velocity v1 initial. And let's say that mass 2 is moving with the velocity v2 initial. And so so they're going to collide somewhere, and once they collide, then they're going to stick together. So now this is going to be mass 1 and mass 2, and they're going to move with the same final common velocity, which I'll call v final. So now we're going to apply conservation of momentum. What that says is that the total momentum before the collision, so P total initial, is equal to momentum 1 initial plus momentum 2 initial, and that is equal to mass 1 times v1 initial plus mass 2 times v2 initial. And the total momentum after the collision is P total final, and that is just the total mass moving at the common velocity v final. So we're just I'm just going to say m total multiplied by the final velocity. And what conservation of momentum says is that this momentum here before the collision has to equal this momentum after the collision. So for a completely inelastic collision, the equation to apply is mass 1 multiplied by v1 initial plus mass 2 multiplied by v2 initial is equal to the total mass multiplied by v final. The next version of this equation that we're going to look at are for explosions. So what that means is that, let's say that there's a rocket that's flying through the air, and it has different parts. So there's like the small part here, and there's a big part. And so we're just going to assume that it's going to move in a straight line. So this is before the explosion, and then this is going to be after the explosion. So before the explosion, the whole thing is connected, but there's two masses. So there's the big mass, I'll call mass 1 here, and then there's a little mass 2. And because they're both connected, they're moving with the same initial velocity. So v initial is the same for both objects. And now after the collision, the rocket breaks apart. So then one piece falls off here, and then the other piece falls off there, so that they split up. But I'm just going to do it in a straight line. So after the explosion, you're going to assume that the little piece flies forwards and the big piece flies backwards. And so here, the big piece has a mass m1, and it has a velocity after the collision of v1 final. And the little piece has a mass m2, and it's moving with the velocity after the collision v2 final. And again, we're going to say that the total momentum before the collision is going to equal the total momentum after the collision. In this case here, the total momentum before the collision is equal to both of the masses moving at the same initial velocity. So that's going to be total mass multiplied by v initial, that's the same for both, and that's going to equal the total momentum after the collision, which is the combination of these two here. So that's going to be mass 1 multiplied by V1 final plus mass 2 multiplied by V2 final. So this would be applied for whenever something explodes or breaks up into pieces and the pieces fly off in different directions. So I'm just going to call that an explosion.